You've got a temperature sensor that needs to connect 200 meters away from your control room. Now you could run Cat6 Ethernet all that distance, add network switches, manage IP addressing, spend thousands of dollars, or you grab a twisted pair, run it directly, and you're done. Under $100, one afternoon. That's Modbus RTU. Yeah, TCP is growing. It's about 45% of new installations now. But RTU? Still running about a third of active Modbus systems across industry. And I'm telling you right now, you're going to hit it on your job. Guarantee it. Today we're walking through how to make RTU work reliably. Because when you choose simplicity over speed, you've got to get the electrical layer right. Quick clarification before we dive in. Modbus is a family of protocols. I've covered Modbus TCP already. That's different. That runs over Ethernet. What we're talking about today, Modbus RTU and ASCII. These are the serial versions. Both transmit over RS-485 wiring. RTU is binary, fast, efficient. This is what you'll use. ASCII is text-based, slower, legacy, only for special cases like radio links, ancient systems, modem connections. Don't overthink this. Use RTU. The basic model never changes, whether you're using TCP, RTU, or ASCII. A master device asks questions. Slave devices answer. Simple as that. But here's the thing with serial RTU. Those messages travel as electrical signals across physical wires. And that's where the real work is, getting those wires right. Because if you mess that up, nothing else matters. Modbus RTU runs on something called RS-485 serial communication. That's just the electrical standard for how data travels. You've got two wires twisted together, A and B. Why twisted? Here's the thing. When electrical noise from motors or power cables hits your signal wires, that twisting makes the noise hit both wires equally. The receiver only cares about the difference between them. If they both get noisy equally, that difference stays clean. The noise gets rejected automatically. It's elegant engineering. It's why RTU networks work so reliably in dirty electrical environments, factories, not clean offices. They were built for noise. Listen, most RTU failures happen because someone violates one of 4 rules. Just 4. I'm going to walk you through each one, and once you've got these locked down, you'll solve 95% of RTU problems you'll ever encounter. Rule 1, your network is a line, not a tree. Device 1 connects to device 2. Device 2 connects to device 3. Straight line. That's daisy chaining. That's the whole point. Never run a main cable and branch off to devices. Those branches, called stubs, they reflect signals. They interfere with your data. I've walked into plants where someone thought branching was more flexible. It's not. It destroys your network. Rule 2. Termination resistors only at the ends. The very beginning of your line, 120 ohm resistor across A and B, very end. Another 120 ohm resistor. That's it. 2 locations. Total. Why? Electrical signals bounce off on terminated cable ends like echoes. Those reflections crash into incoming data and corrupt it. The resistor absorbs the echo, only at the ends, not in the middle, not scattered throughout. I've seen people add resistors thinking more is better. It's not. More resistors change the electrical load and boom, everything breaks. Rule 3. The bus needs a known idle state. Here's where it gets tricky. When nobody's transmitting, the voltage on the bus needs to be stable, defined, predictable. Why? Because noise can be misinterpreted as actual data. The receiver can think it's receiving a message when it's just electrical noise bouncing around. You add bias resistors. They hold the bus at a known idle voltage. Simple concept. But skip it? I had a client where this was missing. System worked 90% of the time. Then cold weather hit. Someone ran a power tool near the cable. Boom, random errors. Took weeks to diagnose. Rule 4, a third wire, the signal ground. Your PLC is powered by one breaker panel. Your sensor is powered by another across the plant. Those power systems have different ground potentials, maybe a few volts difference. The signal ground wire connects all device grounds together, puts them on the same reference. Here's the thing though, don't just connect it directly. Add a resistor in series, typically between 100 and 150 ohms, depending on your system design. This varies based on cable characteristics and loading, so you might see different recommendations depending on your specific setup. Why the resistor? Prevents ground loop currents while still giving the receiver a voltage reference. It's a balancing act. Alright, so you've got your wiring right. Now comes a choice, RTU or ASCII. RTU is binary. Data goes as raw ones and zeros. Fast, compact. ASCII is text-based. Data gets converted to readable characters. Slower, but forgiving. RTU uses about 11 bits per byte. ASCII uses about 20 bits. Do the math, RTU is roughly twice as fast. For any modern installation, use RTU, period. It's faster, more efficient, more robust. ASCII, only for legacy systems or communication over modems, where connection reliability is shaky. Don't overthink this. RTU is the default. Here's something critical, and understanding this prevents a huge category of failures. When your PLC sends a message, bytes flow one after another across the wire. Now here's the question. When does the receiver know the message is done? RTU doesn't use a special end of message character. Doesn't work that way. Instead, it uses silence. If there's no new data for about 3.5 character times, the receiver assumes the message is finished. At 9600 baud, that's about 4 milliseconds. Why does this matter? Because if your transmitting device pauses for longer than 4 milliseconds in the middle of a message, the receiver thinks the message is done. It stops listening. Then you send more data, and the receiver thinks you're starting a brand new message. Result? Communication failure. And you know what? This happens constantly on Windows or Linux when the operating system scheduler pauses the serial driver for other tasks. The practical fix: make sure your serial port hardware's got a deep buffer. Test your system under load. Make sure those OS pauses don't break your messages. When a message travels across those wires, electrical noise might corrupt it. A bit might flip. A byte might get changed. Modbus includes an error check in every single message. It's called a CRC, cyclic redundancy check. Here's how it works. The transmitter does math on the data and appends a special code. The receiver does the same math and checks if the result matches. They match, data is clean. They don't match, something got corrupted. Discard it and ask for it again. Now, if you're getting CRC errors in your system, listen to me. That's usually a sign of physical layer problems. Bad cabling, improper termination, inadequate shielding. Not a protocol problem. Fix the wires first. Don't waste time chasing protocol issues until you've verified the electrical layer is solid. When RTU stops working, don't panic. Check things in order. I use this exact approach every single time. Step 1, check the wires. Power off. Measure resistance between A and B. Should read about 120 ohms. If it reads something way different, termination is wrong or missing. Power on. Measure voltage between A and B when the bus is idle. Should be at least 200 millivolts. If it's near zero, fail-safe biasing is missing. Step 2. Look at the signal with a scope. A properly wired RS-485 bus has clean, sharp edges. See ringing? Oscillations at the edges? That means impedance problems. Noise that doesn't look like data? EMI is getting through. Visual inspection catches problems software can't see. Step 3, use diagnostic software. Tools like ModScan or Modbus Poll let you see the actual bytes being transmitted in real time. Watch for timeouts, CRC errors, timing violations. So always start with the physical layer first, protocol layer second. I've never seen a Modbus problem that was protocol related when the wires were good. It's always the wires. Look, Modbus RTU is aging technology. TCP is the future. Most new projects moving that direction. I get it. But here's the reality you need to understand. RTU still powers about a third of active Modbus installations across industry. Thousands of existing systems. Retrofit projects, budget-conscious integrations, legacy equipment that works perfectly and doesn't need replacing. When you walk into your first plant job, I guarantee you'll encounter RTU. When you do, you've got to understand it. So what do? You need to master these fundamentals, and you'll solve 95% of Modbus RTU problems. Good wiring, linear topology, proper termination at the ends only, fail-safe biasing, signal ground with series resistance, RTU mode for serial implementations. Understand the timing. That 3.5 character silence rule is real and it matters. Get those right and the rest is just details. If this helped you out, give it a thumbs up and subscribe for more practical videos. A super thanks is an easy way to support the channel as well. Drop a comment. Have you encountered Modbus RTU in your work? What situation made you choose it over TCP? I read every single comment. Thanks for watching. I'll see you next time on Scada and Beyond with Alana.